All right. Last lesson you learned that organic chemistry is based on carbons and hydrogens, but the atoms other than carbon and hydrogen determine what the molecules can really do. So there are several atoms that are important. Oxygens turn out to be very common, very important. Nitrogens, again, very common, very important. Sulfur is more rare, but important. And then we have halogens, common. Halogens are chlorine, bromine, iodine, sometimes fluorine, but rare. And what these do, they provide polarity, which is always important. And they really provide sites where reactions can occur. Reactive, I'll call them sites, positions, maybe that's better. So you have your carbon chain, which is not very reactive by itself, but once you add these heteroatoms is what they're called, oxygens, nitrogens, etc., then you get places where reactions can occur readily. Families of organic molecules. The big idea in organic chemistry is that although there are millions of different molecules, they can be classified, they can be grouped. They are similar. When their structures are similar, their reactivities are similar. So I'm calling these families. Your textbook calls them functional groups. I guess I can do it this way and put both in the same. Functional groups define families. So a functional group is a structural feature, and a family would be molecules that behave in similar ways. For example, oxygen atoms form alcohols. So there's a family of molecules, alcohols. They have a functional group in common, a structural group in common. Also, carboxylic acids rely on oxygen atoms. So this is the idea here. Functional groups define families. Nitrogens, on the other hand, nitrogen atoms are responsible for making what are called amines. And those are an important family of molecules which we'll be using frequently in ACR. Here's an example of what we mean by families and how they behave in similar ways. These molecules here you should recognize as alcohols. Alcohols have an OH functional group. You see up here, there's an OH functional group. Here in the middle, there's an OH functional group right here. So they're both alcohols. The first one's ethyl alcohol. When oxidized, the OH turns into a double bond to oxygen, and there is a loss of two hydrogens. That's what happens with ethyl alcohol. This molecule is called acetaldehyde, and it's an oxidation product of ethyl alcohol. Take a look at the second molecule and see whether you can imagine a very similar process occurring. I'll give you a chance to guess at the product before I show you the answer. Here's what happens. It still has 3 carbons. Oxidation doesn't change that. But where there was an OH and an H, that's replaced with a double bond to oxygen, and the 2 ends stay the same. So this is, I hope, a clear example how, if you know what happens to alcohols when they're oxidized, you can predict the reactivity of thousands of alcohols. This happens to be the molecule acetone, which some of you may recognize as nail polish remover. It's a good solvent. So if you look at the generalization, alcohols can be oxidized. The idea of a family makes it easy to understand the chemistry rather than memorizing a million different examples. Okay, so there are three families that I want you to be able to recognize when you see them in ACR. They're very common. We use them frequently. The first is the alcohols. We've seen examples above. These are carbon bonded to an OH. Often there are hydrogens here, but sometimes this could be a carbon, and this could be anything you want. Rest of molecule. I'll change this into an R prime. But this is what you look for, this OH group, alcohols. Know them when you see them. From the last lesson, you should understand we have things like methyl alcohol. We have ethyl alcohol. We have propyl alcohol. And these all have an OH attached to some number of carbons. The second important group I mentioned above, amines. Amines will be related to ammonia. Ammonia was NH3. And now imagine replacing one of those hydrogens with a carbon group. So this R is a carbon group. We're talking about organic molecules. And now we have an amine. We could have ethylamine if the carbon group were 2 carbons. Then we have ethylamine. If the carbon group was 5 carbons, we have pentylamine. Sometimes we have di-substituted amines where you have your N attached to carbon group number 1 and carbon group number 2, and sometimes even carbon group number 3. So you could have like diethylamine. Diethylamine would be two copies of 2 carbon groups. So 2 carbons there, 2 carbons there. Diethylamine. The third group that's very important for you to recognize are carboxylic acids. You saw these in sophomore chemistry. Carboxy, carbon and oxygen. This has the structure COOH. Very common, very important. Trigonal planar geometry, rest of molecule here. So the simplest one, it's actually not the simplest, but it's the most common one, is acetic acid. Acetic acid looks like this. It's the active ingredient vinegar. So when you smell vinegar, you're really smelling acetic acid, that molecule. And we can make it more complicated by changing this R group. We could make it be 17 carbons. If it has the COOH, it is still a carboxylic acid. Other carboxylic acids you would recognize by name: citric acid, which is found in lemons and oranges and limes. Benzoic acid, you should remember from sophomore year. Benzoic acid, you can imagine benzoic acid must have a benzene ring here as the R group. And so that's where the name, if you understand some of the basic names, it helps you understand the structures.